In this video, we're going to take a look at an example of an optimization problem involving distance, speed, and time. So we have a man that's on an island that's 4 kilometers from the nearest point on shore. Okay, so I've kind of drawn it out right there. We've got a man, he's 4 kilometers from the nearest point on shore. The nearest point on shore will be the distance that is perpendicular to the shore. He wants to go to a house which is 8 kilometers along the shore from that point. So we go over here and the house is right here, 8 kilometers from that point on shore. He can row at 3 kilometers per hour and walk at 5 kilometers per hour. Where should he land if he wants to reach the hotel as soon as possible? So you might be thinking, well, can he just row across and walk south? Yeah, that's one possibility. The other possibility would be for him to just go ahead and row directly to the house. The only issue there is that his rowing speed is quite slow. So that might not be the best way to go about it. Okay. So ideally, what makes this an optimization problem is that he is going to go to some point on the shore and then he's going to walk the rest of the way. Okay. So we're going to try and optimize that. All right. And so just for context, this is just water all along here. Okay, there we go. All right. Okay, so we're going to try and find what's this distance here he should row, right? And then this distance right here will make this distance y right here. So then this distance should be 8 minus y because the entire distance is 8. And if this is y, then this distance right here is 8 minus y. Okay, so let's go ahead and set up some equations. Well, we know that distance is equal to speed times time. This means that time is equal to distance over speed. We know that the time he spends rowing, time spent rowing, would be the distance that he rows over the speed that he rows. So if he's rowing, the distance that he rows is 8, and the speed that he rows is given in the question, that's 3. The time spent walking is given by this equation, and walking would be 8 minus y, that's the distance, right? If he lands here, then the distance to the house is just 8 minus y, over the speed at which he can walk, which is 5 kilometers. So I'm going to create a function, okay? I'm going to say let t represent the total time traveling. So that means that that function is a combination of his time spent rowing plus his time spent walking. But you may have picked up on the fact that this is a right-angled triangle, which means that we have another equation. And we should have another equation because we have two unknowns here. We have x and we have y. So I need to figure out how to get one of these unknowns in terms of the other. Well, using Pythagorean, I know that x squared would be equal to 4 squared plus y squared. So that means that x is equal to the square root of 16 plus y squared. So I can restate this function as therefore time is equal to, and instead of writing square root, what I'll write instead is I'll write 16 plus y squared, here we go, 16 plus y squared raised to the power of 1/2, all divided by 3. So that's just a replacement for x. Okay, I'm just substituting x in there. All right, and then I have still over here 8 minus y over 5. Okay, so the total time is now expressed solely in terms of y. And what I'm going to do is I'm going to try to find the minimum time spent traveling. So to find the minimum time spent traveling, what I'll do is I'll take the first derivative and I'll set it equal to 0 to find the minimum. So let's take the first derivative of this. This might be a bit complex, but bear with me. All right, so the first derivative is equal to, okay, see how this is all over 3? Well, I'll just make that a coefficient in front. Then I recognize that the 1/2 has to come down in front. I keep the inside function the same. I reduce this by 1, so I get minus 1/2. Then I have to use the chain rule and take the derivative of the inside function, and the derivative of the inside function is 2y. Then over here, this right here is the same thing as saying 1 over 5, and then the derivative of 8 minus y, well, that's just equal to -1. Okay, the derivative of this right here is just the coefficient in front of y, which is -1. So I'm going to clean this up just a little bit. I'm going to get rid of this 2 right here. I'll get rid of this 2. Okay, and then I'm going to write t prime is equal to, and then I'll have y is going to be in the numerator, right? 3 is going to be in the denominator, and then I'll have this square root of 16 plus y squared all in the denominator because it was -1/2. And then over here, then I also have to recognize that I've got minus 1/5. All right? Now, I'm going to scooch this over to the side so that I can keep going. There's a lot of work that needs to be done here. Remember, I need to set my first derivative equal to 0 to find the minimum. All right, so here we go. I'm going to set it equal to 0. 0 is equal to y over 3 square root 16 plus y squared, right? And then minus 1 over 5. Okay, I'm going to bring the 1 over 5 to the other side. 1 over 5 is equal to y. Again, that's not an index. That's literally 3 times 16 plus y squared. I'll just try and make that a little bit clearer over here because it kind of looks like an index right there. And it really is just a coefficient in front of that square root symbol. Okay, so there we go. I got that 1 over 5 right there. Okay. Then what I'm going to do is I'm just going to multiply both sides by 5. And I'll multiply also both sides by this denominator. So I'm just going to essentially get rid of my fractions. So multiplying both sides by 5, that gives me 5y. And multiplying both sides by this denominator would eliminate the denominator here. And then I have 3 times the square root of 16 plus y squared. Okay, I have to get this all sort of by itself, right? I want to get this by itself, so I'll do 16 plus y squared is equal to, and then I have 5y over 3, and I want to get rid of this square root symbol. So what I'm going to do is I'm going to square both sides of the equation, and then I get 16 plus y squared is equal to 25y all over 9. Okay, what I will do here is now that I've got, this should be 25y squared, apologies. Okay, all right, so I've got these y squareds. Let me get rid of this 9 over here. So I'm going to multiply everything by 9. If I multiply everything by 9, well, 16 times 9 is 144, plus 9y squared is equal to 25y squared. So I cleared the fraction by multiplying both sides by 9. If you want, I can show that right here. Okay, that allows me to clear that fraction. Okay. So still quite a lot of math here, right? I'm just moving things around trying to get y by itself. 144 is equal to 25y squared minus 9y squared. So then I've got 144 is equal to 16y squared. And then I'm just going to jump and say that this right here is equal, y squared is equal to 9. And then I'll say y is equal to 3. Y should be equal to plus or minus 3, but I know I can throw out the -3 because it has no context in this question. Okay, so I have right here, okay, that y would equal to 3 to give me the minimum amount of time. But I actually need to test out a whole bunch of different options. So this is what I'm going to test out. I'm actually going to test out when y is equal to 0. Well, if y is equal to 0, then effectively this whole space right here goes to 0, and the person is just going 4 kilometers across and 8 kilometers down. Okay, so I'm going to test the extreme. So I'll show you what I'm testing right here. I'm going to test when y is equal to 0. If y is equal to 0, then x is equal to 4. And the time taken would be 4 over 3 plus 8, and y is 0, so 8 minus 0, all over 5. So time would be approximately equal to 2.93 hours. The other thing that I could do is I can test y is equal to 3. That's what I got when I set my first derivative is equal to 0. All right. And if y is equal to 3, right? If y is equal to 3, then x is equal to 5. Okay, so t is equal to 5 over 3 plus 8 minus 3 all over 5. T is equal to approximately 2.67 hours. All right. Now, the other possibility is if y is equal to 8, which means that the person is going from the island and rowing directly across. So that's when y is equal to 8. It's the entire distance there, right? This person is doing no walking, okay? So test y is equal to 8. If y is equal to 8, then x would be equal to the square root of 80. If you're wondering where I'm getting this, I'm literally just using this equation here to find out what all the other x values are, right? So if y is equal to 8, then x would be the square root of 80. So then time would be the square root of 80 all over 3 plus 8 minus 8 all over 5. So the time there, if the person just rows directly, is 2.97 hours. Well, we can see that the extremes do not give us the fastest possible option. What gives us the fastest possible option is when we optimized, when we took the first derivative, set it equal to 0, and we found that y is equal to 3. Okay, so we can write our therefore statement here. So here we go. Therefore, the person should row 5 kilometers, right? That's because x is equal to 5. That's x is equal to 5. Row 5 kilometers and walk. Think about it. Walk is going to be 8 minus y, which is 3. So 5. So walk 5 kilometers. Okay? And the trip would take 2 hours and 40 minutes. You might be wondering, where am I getting this 40 minutes from? Well, it's 2 hours, and 0.67 is basically your decimal version of 2/3. Well, 2/3 of an hour is 40 minutes. All right, so a lot going on in this question. Effectively, you want to set up your diagram something like this, okay? You want to make sure that you're using contextual clues like this concept of walking and rowing. So you're using time is equal to distance over speed. If this was a cost problem, you'd have to actually look at different equations for that. There isn't such an example right here. Question 8 is a cost problem, so we're not going to use. It's a similar setup but different equations. Okay. And then again, we found our total time. We minimized the total time by taking the first derivative, setting it equal to 0, finding out what our y value is. Then once we found out what our y value is, we were able to find out what our x value is, and then test out the extremes to see which one is the best option. And we can see it is, in fact, when we optimize. Okay, so that's how you do that question. Thanks again for watching, and I'll see you in the next one.